You and I, we do it all day, every day, without even a second thought. We open our eyes, and the world just makes sense. But have you ever stopped to wonder how you teach a computer to do that? How do you teach a machine something as simple and yet as incredibly complex as just seeing? Well, today, that's the exact journey we're going to go on.
All right, let's get right to it. How can a computer tell the difference between a cat and a fish? I mean, for us, it's instant. That's a cat, that's a fish, no problem. But for a computer, these are just grids of numbers, a sea of pixels that have zero meaning on their own. The real challenge, the whole puzzle, is bridging that gap from raw data to an actual concept like cat. The old school way of trying to solve this was to write a mountain of rules. If it has whiskers and pointy ears, then it's a cat. If it has scales and fins, it's a fish. But that approach is just so brittle, right? I mean, what if the cat's ears are folded down? What if you can't even see the fish's fins? The whole thing just falls apart. So the modern approach, deep learning, it just flips this whole idea on its head. Instead of feeding the computer a bunch of rules, we give it thousands and thousands of examples and let it figure out the rules for itself. So if we're going to teach a machine by just showing it a ton of examples, our first job is to really get what that means. It sounds easy, but doing it right is the foundation for everything that comes next. We're starting with what can feel like an impossible task. And this right here is the absolute key. For a machine learning model, experience doesn't mean going out into the world. Its experience is data, huge amounts of data. The code we write, that's like the engine. But the data is the fuel, it's the textbook, and it's the teacher, all rolled into one powerful package. And this big collection of data has a name. It's called a dataset. And listen, it's not just some random folder of pictures you scraped off the internet. It's carefully curated. Every single image has to have a correct label. This picture is tagged cat. This one is tagged fish. That label is just as important as the picture itself, because that's the ground truth. That's the answer key the model is going to learn from. But here's the thing, we can't just dump all our data into one big bucket and hope for the best. To do this like a pro, we have to be smart about it. We split our data into 3 different piles. First up, you've got the training set. This is the main textbook our model's going to study to learn all the patterns. Then you have the validation set. Think of this like a series of pop quizzes. We use it to check in and see how well the model is learning, making sure it isn't just memorizing the answers. And finally, the test set. This is the final exam. It's kept under lock and key until the very end, so we can get a totally unbiased grade on how well our model really learned.
Okay, so we've got our strategy all mapped out. We're going to train, we're going to validate, and then we're going to test. That brings us to our next phase. We've gathered the raw materials, and now it's time to build the mind that's going to learn from it all. And the amazing tool we're going to use for this job is the star of our show, the Convolutional Neural Network, or CNN for short. And what's so cool about CNNs is that they're directly inspired by how our own brains process vision. I mean, it's basically an artificial brain, specifically built to see. So how does a CNN actually see? It's this really fascinating layered process. Okay, so step 1. A tiny little filter scans the image, and it's looking for something super simple, like a straight edge or a little curve. Step 2, it slides that filter across the entire image, basically creating a map of everywhere it found that one simple feature. Step 3, and this is where the magic really happens. Deeper layers in the network take those simple maps and start combining them to find more complex things, like an eye or a whisker or a fin. And then finally, step 4, the last layers look at all these complex features that have been found and learn how to put them all together to make that final prediction. Yep, that's a cat, or no, that's a fish. And that whole process, that step-by-step system of filters and layers, that's what defines the structure of our model. We are, quite literally, building the brain that's about to do all the learning. So our digital brain is built, our data is ready to go, and now the real work starts. This is where the training begins. The model is shown an image from our training set, it makes a guess, it checks the label, it's probably wrong, especially at first. So it learns a tiny bit from its mistake, and then moves on to the next image. This happens thousands, even millions of times, in this super fast, repetitive cycle. So you might be wondering, how does it know how wrong it is? Well, that's the job of something called the loss function. The best way to think about it is like a very strict teacher with a big red pen. It calculates a score for every single guess. If the model is super confident it's a cat but the label says it's a fish, the loss function gives it a really high error score. The model's entire goal in life is to get that score as low as it possibly can.
Right, so if the loss function is the teacher that says, hey, you got that wrong, the optimizer is the study guide that shows the model how to get better. It takes that error score, and using some really clever math, it makes thousands of tiny little adjustments to the connections inside the network. Each little tweak is perfectly designed to just nudge the next guess a little bit closer to the right answer.
And when you put it all together, the guessing, the checking, the adjusting, and you do that over one full pass of the entire dataset, which we call an epoch, something incredible starts to happen. And this chart shows it perfectly. Look, after the first epoch, the error is still sky high. But by epoch 10, it has absolutely plummeted. And by epoch 20, the model is consistently making really solid predictions. It is actually learning.
This whole process, this relentless cycle of guessing and improving, that's what we call training. It's basically our model's version of a Rocky-style training montage, just getting smarter and stronger with every single example it sees.
But now comes the moment of truth. After all of that training, all that learning from thousands and thousands of examples, it is time for that final exam. We take an image from our test set, and remember, this is brand new data the model has never, ever seen before, and we ask it one simple question. What is this? And the model, because it's learned the abstract patterns of fins and scales and fish-like shapes, makes its prediction. Fish. Success! The entire journey, all the way from gathering data to tweaking the network, it all paid off. Okay, so that is an incredible achievement. But the real power of this technology goes so much further than just telling cats from fish. And that takes us to our final section, where we see how this one simple ability builds into something truly world-changing. The source material we're using for this explainer puts it just perfectly with this one idea. A network trained for one task is adapted to another. This single concept is honestly one of the biggest breakthroughs in all of modern AI.
And it's called transfer learning. Think about it. Why would you teach a brand new model what an edge or a curve or a texture looks like from scratch when these huge models, trained by giant research labs, have already learned those fundamental visual features from looking at millions of images? So transfer learning is the ultimate shortcut. We take one of these expert, pre-trained models, and we just retrain the very last couple of layers for our specific task. We're not teaching from scratch. We're giving an expert a new specialty.
So, why does this matter? Well, this changes everything. It saves an absolutely immense amount of time and money. It lets us tap into the knowledge from datasets that are way larger than anything we could ever build ourselves. We can get incredibly high accuracy with way less of our own data. And this technique, this is what powers countless real-world AI tools that you probably use every day, from the camera on your phone to advanced medical imaging systems.
So we've started with a pretty simple question, and we followed this whole journey all the way to an answer that has completely reshaped our world. And that leaves us with one final, much bigger question to think about. If a machine can truly learn to see a cat, what else can it learn to see? And more importantly, what else can it learn to do?